What is a mathematical proof? Loosely speaking, it's an argument or a verification of a mathematical fact. That fact is typically called a theorem. And that's usually our goal with mathematical proofs, to prove theorems. Sometimes we'll use other words as well, like lemma. A lemma is often described as a helping theorem, or a little theorem that helps us prove a bigger theorem, something we're actually trying to prove. Maybe we'll look at a corollary, which is a direct result following from a proved theorem. Sometimes less important theorems are called propositions, and there are many conjectures out there. Those are statements that are proposed to be true, but might turn out to be false. Once a proof is found, then we'll call it a theorem. How exactly do we go about proving these theorems? Mainly we'll use definitions, rules of logic, maybe some other theorems, and axioms. Axioms are statements which are given to be true. We assume them. We can't prove them. What does a mathematical proof look like? Generally, it's a series of statements, each which logically follows from what came before. We start with something we're assuming to be true, and logically proceed until we get to our conclusion, that conclusion being the thing we're trying to prove. Much like a good story, proofs have a beginning, a middle, and an end. The beginning is what we assume to be true. These might be definitions or axioms. The middle are the logical statements, and the end is the theorem, the conclusion, the thing that we're trying to prove. What's very interesting about this process is that it's unlike math problems you may have come across before. In a typical math class, you would be given the problem and asked to work out the solution. With a mathematical proof, we know what the solution is. We pretty much know what we're looking for. We also know what the assumptions are at the start. And our job is to create the bridge from the assumption to the conclusion via those logical statements. What sort of theorems are we trying to prove? There might be a wide variety of things you're trying to prove, but some common ones are when two things are equal, when one thing implies another, when one thing implies another and the other implies the one, a certain object has a certain property, or maybe that all objects of a certain kind have a certain property. You could be trying to show that something exists, or maybe even that something exists and it's the only one that does exist. We'll be exploring all of these ideas and more throughout the course, but right now I want to get our hands dirty with your first mathematical proof. Let's prove the theorem that the square root of 2 is an irrational number. This is the fact that we're trying to show is true. And already there's some implicit definitions going on here. You have to know what an irrational number is. An irrational number is a real number which can't be written as a fraction, or we might say it can't be written as m over n, where m and n are integers. Notice how precise and abstract that definition is. That's quite common when we define things in math. We can say exactly what something is in general. Now that we have our definition, on to the proof. Here's one way to do it. We want to show that square root of 2 is in fact irrational, but suppose it wasn't. This is our assumption. supposing that the square root of 2 is not irrational. What does that mean? Following from our definition, if square root of 2 is not irrational, that is, it's rational, it can be written as a fraction. That is, square root of 2 can be written as m over n, with m and n being integers. Now there's also a very subtle yet important implicit thing going on here. This fraction is in its most reduced form. So we're assuming that square root of 2 equals m over n, m and n being integers, and this fraction is reduced. We've made all of the assumptions and we've written all the definitions we need. It's on to the logical process. So what steps can we take from here? Maybe the square root of 2 is a little bit tougher to work with algebraically. How about we square both sides of this equation? Just remembering rules of exponents. If we square square root of 2, that's just 2. M over n all squared means the same thing as m squared over n squared. And we can rewrite this equation a little bit more nicely as 2n squared equals m squared. What's the consequence of this? Well, are you ready for another definition? What's an even number? If you've never thought about this before, it might seem obvious. It's any number which is divisible by 2. A mathematician might say that an even number can be written as 2 times another number. And this is that exact situation. M squared is twice another number. That means m squared is even. Well, if m squared is even, m itself must also be even. And if m is even, then m can be written as 2 times some other number. Let's call it k, where k is an integer. Now we have a new representation for m. Let's plug this back into our equation. We have 2n squared equals 2k now squared. Applying properties of exponents, 2n squared would be 4k squared. And dividing both sides by 2, n squared equals 2k squared. What's the next consequence of this? Pause your video and think about the conclusion we made before. N squared is written as 2 times a number. This means that n squared is even, and also that n is even. What's the conclusion of these two finds? We had that m is even, and n is even. Well, if m and n are both even, then their fraction, m over n, should be reducible. We should be able to reduce it since they're both divisible by 2. Yet that violated our original assumption. We had that assumption that m over n was a fraction written in lowest terms. Or in other words, our assumption was that the square root of 2 was rational. And by assuming that the square root of 2 was rational, and via a correct logical process, we came up with something that was self-contradicting. So what went wrong here? Was our logic wrong? Was our math wrong? Was anything in our process wrong? Well, nothing about our logical process was wrong. What must be wrong was our assumption. If everything in our logic is correct, yet we have a contradiction, it must be that our assumption was wrong. It can't be true that the square root of 2 is rational, meaning the square root of 2 is irrational and the theorem is proved. Sometimes when we complete a proof or we want to show that something is proven, we'll write a little box next to it. This says, hey, we're done. Our argument is complete. I hope you stuck in there for that. And if this is your first time seeing this proof or any mathematical proof, and it didn't quite sit right, I don't want you to get discouraged. It takes a while for these proofs and these proof ideas to really sink in. I'm confident that after moving through this course and getting a little bit of practice, you're going to feel much more comfortable with mathematical proof.
In this video, we'll discuss the logical rules and logical inferences made when doing proofs. Typically, when we write proofs, we don't literally reference these. They're almost taken for granted. They're ingrained in our knowledge. You don't need to know these by name, and the more you work with them, the more obvious and logical they will become. Here's our first rule, modus ponens. This is the situation where if P is true and P implies Q, then Q is also true. The notation here is P, representing P. P right arrow Q, this is the notation for P implies Q. The 3 dots is typically therefore and Q. Here's an example. P is the statement, it is raining. Q is the statement, the ground is wet. Given P, given it is raining, and given the implication, if it's raining, it implies the ground is wet. What's the conclusion? The ground is wet. Modus tollens is our next rule. It says, if not Q is true, and P implies Q, then not P is true. This is sort of the reverse of our last rule. Here's the notation. We have this dash Q. This means not Q. P arrow Q means P implies Q. The 3 dots mean therefore. Dash P means not P. Here's our example. P again is the statement, it is raining. Q is the statement, the ground is wet. Given the ground is not wet, and this implication that it's raining implies the ground is wet, what's our conclusion? It's not raining. And this makes logical sense. If we have this implication and the ground is not wet, it must be the case that it's not raining. Here's the next one, hypothetical syllogism. This is sort of like a chain of reasoning, that one thing implies another, and the another applies another all the way down. The notation looks like this. P implies Q, Q implies R, therefore P implies R. Here's our raining example. P is it's raining, Q is the ground is wet, R is people use umbrellas. Given the following, these implications, it's raining implies the ground is wet, the ground is wet implies people use umbrellas. What's the conclusion here? Well, if it's raining, then people use umbrellas. Disjunctive syllogism can be very powerful, but maybe a little bit more confusing the first time you see it. I promise the more you work with it, the easier it'll be. Here's how it works. If not P is true, also P or Q is true, it must be Q is true. This is like saying one thing or the other is true, but not the one thing is true. It must be that the other thing is true. The only thing we haven't seen in terms of the notation yet is that upward facing V. That's the or in this case, P or Q. Here's our raining example. P is it is raining, Q is I will stay indoors. Given the following, what's the conclusion? We're given it is not raining, and it's raining, or I will stay indoors. What's the logical conclusion? Well, it's either raining or I'll stay indoors, and it's not raining. The conclusion is I will stay indoors. Addition essentially says we can add on or quantifiers to anything, really. Basically, if P is true, then P or Q is true. And here, remember, we're using the logical mathematical OR. This is a non-exclusive OR. OR here could mean both. The notation is P, therefore P or Q. In our example, P is it's raining, Q is I will go for a run. Given that it is raining, what conclusion can we make? Well, it's either raining or I'll go for a run. Basically, if one is true, then one or the other is true. Simplification is sort of the reverse to that. It says if P and Q are true, then P is true. Basically, if both statements are true simultaneously, then each are true by themselves. The notation is the upside down V. This is P and Q, therefore P. Our example, P is it is raining, Q is the ground is wet. Given that it is raining and the ground is wet, what's our conclusion? Well, you could really make two conclusions here. The one that I listed is it is raining. If it's raining and the ground is wet, it's raining. Although you could also conclude simply the ground is wet. Our last rule, conjunction, is very similar to the idea of addition and simplification. Basically, if P is true and Q is true, then P and Q are true, which sort of just feels like a little bit of English moving words around. But here, this has a logical significance. Basically, if P is true, Q is true, therefore P and Q are true. This is the logical and. The example, it is raining is P, the ground is wet is Q. Given it is raining, the ground is wet, what's the conclusion? It is raining and the ground is wet. I'll remind you that when we're doing mathematical proofs, we typically don't cite these logical rules. They're sort of working beneath the surface and taken for granted. So you'll want to keep watching the videos in this series. It's only logical.
Let's talk about sets. What are sets? Well, a set is simply a collection of objects. We usually denote sets with these curly braces. Maybe we're talking about the collection of triangles, maybe the collection of a certain group of numbers, maybe a collection of the real numbers. A set could apply to all of these. You may see sets defined in a couple of different ways. One way is simply a verbal description, like the set of all positive even numbers. Or we could list them in the curly brackets like this, 2, 4, 6, 8, and so on. When mathematicians use this ... notation, we're basically saying this pattern repeats. So this is listing all of the positive even numbers out forever. Quite often we'll use set builder notation for describing sets. This uses the curly braces and tells us what the set contains under a certain condition. For our example, our set might be X such that, or given that, X is even and X is positive. The vertical bar, or sometimes a comma, tells us that this is the restriction or the condition for something to be in the set. Any object inside a set is called an element, or a member of the set. This symbol means the element is in the set. For example, 2 is an element of the set we've described. And this symbol with a slash through it means it's not an element of the set. So 3 would not be an element of our described set. Generally, capital letters are used to describe sets, and lowercase letters are used to describe the objects within the sets. And for very important special sets, we'll often use special notation. Here are some very common sets that you should be familiar with. N is the set of natural numbers, also known as the counting numbers. This is starting at 1, 2, 3, and so on forever. Sometimes we'll say W are the whole numbers, which are just the natural numbers with the inclusion of 0. We have Z, the integers. These are all of the whole numbers, but also the negative whole numbers. Q is the rational numbers. Those are all fractions, P over Q, where P and Q are integers. So rational numbers are ratios of integers, provided of course that the denominator isn't 0. Then there are irrational numbers, which are numbers that can't be written as a ratio of two integers. Something like the square root of 2 would be in here. And then you may be familiar with the real numbers. The real numbers are the combination of the rational numbers and the irrational numbers. These are all numbers which can be represented as a decimal. You may deal with the complex numbers, which are the real numbers with the inclusion of the square root of -1. We call that I. The complex numbers are also known as the imaginary numbers, and it's a beautiful subject if you ever get the chance to study it. There are some other types of sets you should be aware of. The empty set, denoted with an O with a slash through it, or empty curly braces, is a set which contains nothing. This will be a useful concept for some of our set algebra. Also, the universal set is the set of all objects we're currently discussing. For example, if we're talking about dogs, then the universal set would be the set of all dogs. The cardinality of a set, denoted with absolute values typically, describes the number of elements in a set. If the cardinality of a set is a whole number, we call it a finite set. Otherwise, we call it an infinite set. Something to note here is that sets don't care about repetition or order. They're just a collection of objects. So we could have the set 1, 2, 2, 3, 3, 3, 4, 4, 4, 4. This would also be the same as the set 4, 3, 2, 1. Now I just said that these sets are the same. Those sets are equal. So what's the definition of set equality? Well, two sets are equal if every element of A is an element of B, and every element of B is an element of A. A mathematician might say that each set is a subset of the other. A set is a subset when every element is in the other set. For example, the natural numbers are a subset of the whole numbers, since every natural number is a whole number. However, we couldn't say that the whole numbers are a subset of the natural numbers because 0 is a whole number, but 0 is not a natural number. The power set of a set is a special set. The power set is the set of all possible subsets. Now that's a strange definition in itself. It's a set of sets. For example, if we had the set 0, 1, then the power set would be the set of 0, the set of 1, the set of 0, 1, and also the empty set. Why are all of these inside of the power set? Well, each of these are a subset of the set 0, 1. The set containing 0 is a subset of 0, 1. The set containing 1 is a subset of 0, 1. The set 0, 1 is technically a subset of 0, 1, since every element of 0, 1 is in 0, 1. And by definition, the empty set is also a subset of 0, 1. The complement of a set, denoted with an upper C or an apostrophe, is all of the elements which are not in the set, with respect to the universal set. Sometimes we describe this as a set difference. It's kind of like a subtraction with sets. This says take all the elements in a set, but take out all of the elements in the other set. So the complement of a set A would be all the elements in the universal set less all the elements in A. For example, take the rational numbers with the universal set being the real numbers. What would the complement of the rational numbers be? Well, it's all of the real numbers, but not all of the rational numbers. What are we left with? We're left with the irrational numbers. You could talk about the whole numbers with respect to the integers. What would the complement of the whole numbers be? Well, it would be all of the integers less all of the whole numbers, and you would be left with a set of all negative integers. If we want to combine two sets, we can take their union. The union of two sets is the set of elements belonging to either of the sets. Or using our set builder notation, A union B are all elements X, given that X is in A or X is in B. Typically when we're doing unions, we don't have repetition of elements if they're in either set. The intersection of two sets is the set of elements which are common to both sets. Or using the set builder notation, A intersect B are all elements X, given that X is in set A and X is in set B. Here's a quick example. Take the sets 1, 2, 3 and the sets 3, 4, 5. What would be their union? Well, we would take elements from both sets. If we took their union, it would be all the elements of A and all of the elements of B. So the set would be 1, 2, 3, 4, 5. Notice how we didn't repeat 3, even though it was in both sets. The intersection of these two sets would be simply the set containing 3. The intersection is the overlap, any elements which are in both sets. If we changed this slightly to the sets 1, 2, 3 and the set 4, 5, trying to take their intersection now would give us the empty set. These two sets have no elements in common, and so their intersection is empty. When we have an empty intersection, we call these two sets disjoint. Those were a lot of definitions in a very short time, so I would encourage you to review this video at your leisure. It'll be important not only going forward throughout this course, but all along your mathematical journey. Let's do a quick proof with sets. Let's let A, B, and C all be sets, and let's show that if A is a subset of B and B is a subset of C, then A is a subset of C. You might call this the transitive property for sets. This is what we have. We're assuming that A is a subset of B and that B is a subset of C. What do we want to show? We want to show that A is a subset of C. What does that mean, A being a subset of C? That means any element of A is also an element of C. The way that we typically attack these set proofs is to choose an arbitrary element in a set. So let's let little a be an element of capital A. By assumption, A was a subset of B, which means that if little a is in capital A, little a is also in B, since capital A was a subset. We have that the element a is in the set B, and we also assumed that B was a subset of C, which means that every element in B is also an element of C. Hence, a is in the set C. We did this for an arbitrary element, so every element in A is an element of set C. This is what we wanted to show. A is a subset of C. I hope you get lots of practice with set notation and set algebra. Once you do, I think you'll be all set. When doing mathematical proofs, sometimes we come across the same phrase or idea so often we have special symbols for them. These two phrases are very special quantifiers that you'll see all across mathematical literature. The phrase for every or for all is called the universal quantifier and is usually displayed with this upside down A symbol. The phrase there exists is called the existential quantifier and is denoted with this backwards E symbol. We can use these symbols to say mathematical statements. For example, there exists an x such that x plus 3 equals 5. That's a true mathematical statement because there does happen to be an x which exists that satisfies this equation. We also might say something like, for all real number y squared is positive, or at least 0. That again is a true mathematical statement because every single real number, all of them, when squared, is positive, or at least 0. It will also be very important for us to be able to negate our mathematical statements. When we say negate a statement, we don't mean the negative in the sense that the English language uses. We're talking about the logical negation of a sentence. For example, the sentence, that thing is a dog, has the negation, that thing is not a dog. Sometimes you'll see this tilde symbol meaning negation, or sometimes a prime symbol. Here are some other very common negations that you'll see. The statement A or B, its negation is not A and not B. Intuitively, we think of this as either A, either B, or both of them as the statement, where its negation would be neither of them. The statement A and B is negated with not A or not B. The statement if A then B is negated by A and not B. If we think of if A then B as an implication, if A happens then B happens, the negation of this should be that A happens, but B does not happen, hence A and not B. What's very interesting about the universal and existential quantifiers for all and there exists is that they happen to be negations. What I mean is, if we have the statement for all x, y, the negation is there exists an x such that not y. See how we negated the for all, the universal quantifier, with there exists, the existential quantifier. It works the other way too. If we have the statement there exists x such that y, the negation is for every x, not y. Notice how we have to negate each part of this sentence, and notice how the negation of for all is there exists, while the negation of there exists is for all. Let's get some more practice turning statements into symbolic notation and then finding their negation. Here's a statement. For all capital M in the real numbers, there exists a little x in the real numbers such that the absolute value of f of x is greater than or equal to m. What's the symbolic notation here? Well, we'll use the quantifier for all m, in the real numbers. We would use this symbol to mean is an element of, and the R for real numbers. This says for all m in R. Next, there exists, we'll use the existential quantifier, there exists little x in R, such that is displayed in a couple of different ways depending on who you're talking to. More than likely, I'll just write the words such that or capital ST. The last part is just the function in absolute value is greater than or equal to m. This is the symbolic notation of our sentence. Now let's find the negation. We need to negate each part. The negation of for all m in R is there exists an m in R. Remember that the negation of the universal quantifier for all is the existential quantifier there exists. Next, negate the statement there exists x in R. Well, the negation of the existential quantifier is the universal quantifier. It's for all x in R. Now we need to negate the statement the absolute value of f of x is greater than or equal to m. What's the negation of something being greater than or equal to something else? It's that something being less than the something else. So our negation is there exists an m in R such that for all x in R, the absolute value of f of x is less than m. Let's try another one. The statement is, for all m in the real numbers, there exists a little x in the real numbers, such that for all y greater than x, we have f of y is greater than m. What's the symbolic notation? Again, we have the words for all. We'll write the universal quantifier for all m, and we'll use the symbolic notation for an element being in the real numbers. Next, we see there exists. That's the existential quantifier. X is a real number. We can either just say such that or st. For all, again, is the universal quantifier for all y greater than x. The conclusion, f of y is greater than m. This is our symbolic notation of this statement. What's its negation? We have to negate the statement for all m in R. It's there exists an m in R. Next, negate there exists an x in R. The negation is for all x in R. The next one's a bit tricky because we're negating for all y greater than x. You might be tempted to switch the symbol of the inequality here, but that's not exactly what's going on. We're negating a universal quantifier. So the negation is the existential quantifier. The negation is there exists a y greater than x. And then the conclusion, here is where we negate this inequality sign. F of y is greater than m. The negation is f of y is less than or equal to m. Notice the change in the inequality direction and changing from a strict inequality to a less than or equal to symbol. Let's try one more challenging one. Here's the statement. For every epsilon greater than 0, there exists a delta greater than 0 such that the absolute value between f of x minus f of x naught is less than epsilon whenever the absolute value of x minus x naught is less than delta. Okay, let's break this down. For every means for all little epsilon greater than 0, there exists, that's the existential quantifier, delta greater than 0. This is where it gets a little bit tricky, because we need to write the whenever as an implication. So this is where I might say such that for all x in the real numbers, since I didn't classify where this x came from, x minus x naught in absolute value is less than delta. This comes before the implication, because it comes after whenever. This is saying whenever x minus x naught in absolute value is less than delta, we get the other thing. So this implies the absolute value of f of x minus f of x naught is less than epsilon. This is the symbolic notation for this statement. Now, what's its negation? For all epsilon greater than 0, the negation is there exists an epsilon greater than 0. There exists delta greater than 0. The negation is for all delta greater than 0. For all x in R, the negation is there exists an x in R. Here's the real tricky part. We have an implication. X minus x naught less than delta implies f of x minus f of x naught less than epsilon. How do we negate an implication? A implies B is negated by A and not B. So the negation of x minus x naught in absolute value less than delta implies the absolute value of f of x minus f of x naught is less than epsilon is the absolute value of x minus x naught less than delta and not the implication. So the absolute value of f of x minus f of x naught is greater than or equal to epsilon. A implies B is negated by A and not B. This is the negation. Very tricky in my opinion, so I hope you stuck in there and got it. The other videos in this series exist, so I hope you'll watch all of them. Please don't negate my statement. In this video, we'll talk about direct proofs. A direct proof is a verification of a conditional statement. P implies Q. Here we assume that P is true, and through a logical process, we try to verify the implication that Q must be true when P is true. This might be as quick as a one-step implication, or there might be many implications, each following from the previous to get us where we want to go. Direct proofs are some of my favorite because we start with an assumption. That assumption tells us something. That something tells us something else. That something tells us something else. So on and so forth until we get to the answer in a very direct, linear fashion. Let's look at some examples of direct proofs. Here we'll prove that the sum of two even integers equals an even integer. Where do we start? Well, we need to start with two even integers. Call them x and y. We have to be general with this because this has to hold true for any even integer. We can't just use one example. We have to make it arbitrary. Hence, we're using variables here, x and y. What does it mean for x and y to be even? We can say an integer is even if it can be written as twice another number. So we'll say that x is 2a and y is 2b, where a and b are integers. What do we want to show? Well, we want to show that their sum, x plus y, is also even. In other words, x plus y equals twice some integer. We know what we have, we know what we want to show, now we just need to link the two ideas together. And in a very direct manner, we can sort of just crunch this out. Let's just do the algebra. We want to see what x plus y is, so let's compute x plus y. That would be 2a plus 2b, and we need to write this in the form of an even number. How can we do that? Just apply the distributive law, factor out that 2, so x plus y is 2 times the quantity a plus b. Now you might think we're done here. I would go ahead and say one more step. Since a and b are both integers, their sum, a plus b, must also be an integer. Let's just call it p. So now we have x plus y is 2p, where p is an integer, and x plus y is even. Notice how we started by writing the definition of our assumption, and we kept in mind where we were going. Once we knew where we start and where we're going, there was a very direct way of connecting the ideas and finishing the proof. Here's another example. Let's show that an even integer is also even when it's squared. Let's assume that we have an integer m which is even. What does that mean? M can be written as 2 times another number, which is an integer. We want to show that m squared is also even, or in other words, that m squared can be written as twice a number. Now our job is to link these two ideas together. What should we do? Well, the very direct way of doing this is simply to square both sides. Do this algebraic operation. So on the left we have m squared, and on the right-hand side we have 2n all squared. Applying your properties of exponents, this would be 2 squared times n squared, or 4n squared. Now that's not quite the definition of an even number. An even number is twice an integer, and right now we have 4 times an integer squared. But we could simply write 4 as 2 times 2, and say that m squared is 2 times the quantity 2n squared. Now since n was an integer, squaring it and multiplying it by 2 means that's also an integer. We could just call that k. And now m squared is 2k. We conclude that m squared is also even. We've proved this theorem. Here's another very similar but slightly more challenging example. Let's prove that the square of an odd number is also odd. Let's let n be an odd integer. What would that mean? An odd number can be expressed as twice an integer plus 1. So we'll say that n is 2k plus 1 for some integer k. That's what we have to assume. What do we want to show? We want to show that n squared can also be written as twice an integer plus 1. That would make n squared odd. How do you suppose we link these two ideas together? We'll simply do the algebra. Square both sides, so on the left we have n squared, and on the right we have 2k plus 1 squared. Here your rules for remembering how to distribute come into effect. This would be 2k plus 1 times 2k plus 1, which, performing the distribution, 2k times 2k is 4k squared. We'd have 2k times 1, and then 1 times 2k. Finally, 1 times 1. Combine the like terms for this expression. Remember what we're trying to show. We're trying to show that this expression, n squared, can be written as twice an integer plus 1. How do you suppose you could rewrite this? Well, we already have the plus 1 at the end, that's good. So this 4k squared plus 4k, we should rewrite that as twice a number. And just like before, we can factor out a 2 and write this as 2 times the quantity 2k squared plus 2k. And since k was an integer, 2k squared plus 2k must also be an integer. Call it p, and we've written n squared as 2p plus 1 In other words, n squared is odd. We've proved this theorem. I'd like to show you one more direct proof I think every good aspiring mathematician should know, a proof of the Pythagorean theorem. That theorem being that a squared plus b squared equals c squared for a right triangle with legs length a and b and hypotenuse c. This is fairly fun because it involves a very nice picture. Take a look at this square. It's written in such a way that this square has side lengths a plus b, meaning that the area of this square is a plus b times a plus b, or a plus b all squared. And we've inscribed another square inside such that it creates these right triangles and an inner square with side lengths c. So the area of the inside square is c times c, or c squared. Notice how we've constructed the situation we want to describe, a right triangle with legs a and b and hypotenuse c. If we can figure out their relationship directly, we'll have proved the theorem. Here's the neat argument. The area of the square is a plus b all squared. But the area of the square is also the area of the inner square plus the 4 triangles. Each triangle has area 1/2 base times height. In this case, 1/2 a times b. There are 4 of them, so the area of the square is also c squared plus 4 times 1/2 a times b. We can simplify this with our algebra. A plus b all squared expanded would be a squared plus 2ab plus b squared. On the right, we would still have c squared. 4 over 2 is just 2ab. Wouldn't you know it, the 2ab cancels on both sides, and we have the Pythagorean theorem, a squared plus b squared equals c squared. I hope you like the idea of these direct proofs, and if you do and want to learn more, let me direct you to the next video. In this video, we'll learn proof by contrapositive. What's contrapositive, you might ask? The contrapositive is logically equivalent to the conditional P implies Q. P implies Q is equivalent to saying not Q implies not P. We negate each statement and switch the order. These two are logically equivalent, and sometimes one is much easier to prove than the other. A simple example of a contrapositive statement is this. If we have the conditional, if it rains, then I bring an umbrella, the contrapositive would be, if I didn't bring an umbrella, then it's not raining. These two statements are completely logically equivalent. Let's look at a mathematical example. Theorem: if x is an irrational number, then 1 over x is also an irrational number. Remember that an irrational number cannot be written as a ratio of 2 integers. A direct proof here is a little bit cumbersome. If we start with the assumption that x is an irrational number, well, where do we go from here to get that 1 over x would also be irrational? However, we can do this proof by contrapositive. Let's switch the order of these statements and negate them. That would be logically equivalent. So the contrapositive of this statement is, if 1 over x is not irrational, then x is not irrational. If we prove this, it's equivalent to proving what we wanted to prove in the first place. So let's assume 1 over x is not irrational. What does that mean? That means 1 over x is rational, and it can be written as a ratio of two integers. In other words, there exists integers m and n, so that 1 over x equals m over n. Now, with a little bit of algebraic footwork, we can create x all by itself, take the reciprocal of both sides, so that x is the same as n over m. And hey, wouldn't you know it, x has been expressed as a ratio of two integers. N and m were those integers. Hence, x is rational. We showed that if 1 over x is rational, then x is also rational. The contrapositive of this statement is exactly what we were trying to show. That x not rational implies 1 over x is not rational. Here's another example. Let's let n be an integer, and if n squared is odd, then n is also odd. Again, if you try to direct proof here, you might run into some trouble. If you were to try a direct proof, letting n be an integer, you would say that n squared is odd, or in other words, n squared can be written in the form 2k plus 1 for some integer k, and you would have to try to show that n is also odd. Or that n can also be written in the form 2l plus 1, where l is some integer. And how exactly would you go about doing that? You might be tempted to say take the square root and solve for n, but you're not going to be able to write that in the correct form. Since a direct proof doesn't seem to work, let's try the contrapositive. Let's try to prove that if we assume the negation of the conclusion, it implies the negation of the supposition. That is, let's assume that n is not odd, in other words, n is even, and let's say that implies that n squared is not odd, or that n squared is also even. So, we assume n is even. That means n can be written as twice some number k, where k is an integer. We can create n squared by squaring both sides, so n squared is 2k squared, which, using your properties of exponents, would be 4k squared. And you can use the trick, factor out a 2, and write 4 as 2 times 2k squared. Now n squared is written as twice some other number, twice some other integer, since 2k squared is also an integer. Hence, n squared is even. We've proved that if n is even, then n squared is even. Using the contrapositive, this is logically equivalent to saying that n squared not being even implies that n is not even. Or the original statement, n squared is odd, implies n is odd. Let's take a look at if and only if proofs. When you see the words if and only if, this means a two-way proof. This means that P implies Q, also Q implies P. We signify this with a double arrow. When you're completing if and only if proofs, you have to, well, prove the if and the only if. That is, you need to prove the implication, P implies Q. You also have to prove the converse, Q implies P. In that sense, if and only if proofs are twice as much work as a normal proof, but often one implication gives us clues to how to prove the other. Let's look at an example. Theorem: a whole number is even if and only if its square is even. What should this proof look like? Well, if we have a whole number, call it x, then x being even should imply its square should also be even. But since we added the only if, we should also be able to assume that a square is even, then the number itself is also even. Let's complete this if and only if proof. Assume x is a whole number which is even. What's the consequence of this? X can be written as 2 times k, where k is some integer, or in this case a whole number. We can get to x squared by squaring both sides, so x squared is 2k all squared, or using properties of exponents, 4k squared. To say this is an even number, we need to write x squared as 2 times another number, so we factor out the 2. We rewrite 4 as 2 times 2, so x squared is 2 times 2k squared. And since 2k squared is an integer, or in this case a whole number, x squared is written as twice a whole number, and x squared is even. Now we've only completed half the proof. We usually signify this with a forward implication arrow to show which half of the proof we're doing, but we need to do the second half of the proof as well. Let's write a reverse implication arrow to show which way of the proof we're showing now, and let's assume the other way. Let's let x be a whole number and assume that x squared is even. What's the consequence of this? If x squared is even, it can be written as twice another number k. And remember what we're trying to show. We're trying to show x itself is also even, or that x can be written as twice another number. So it might be tempting to try to square root both sides here, but then we would end up with a square root 2 and a root k, which would not be integers, let alone whole numbers. If we want to show something is even, it has to be twice an integer, not square root 2, square root another number. So we have to be a little more creative than attacking this algebraically. Since x squared equals 2k, k being an integer or a whole number, that means 2 divides x squared. And since x squared means x times x times itself, 2 must divide x or x. Or 2 simply divides x. And since 2 divides x, x can be written as twice some number, twice some whole number or integer. Hence, x is also even, and we've proved the converse. Since we completed this proof both ways, we proved the implication and the converse, we've completed this if and only if proof. Here's another example. Prove that a whole number is divisible by 9 if and only if the sum of its digits is divisible by 9. Since it's an if and only if, we have to prove this both ways. To start, we're going to have to let x be a whole number, and since we're talking about its digits, we'll have to construct it in some way. We have to do this for an arbitrary whole number, so we don't know how long the number is. Let's just let it be a sequence of digits a sub n minus 1, all the way down to a sub naught. This will be the whole number we're working with and a sequence of its digits. Let's start our if and only if proof, and we'll first assume that x is divisible by 9. We're proving this direction of the proof. Let's take our number x and write it in expanded notation. Since these are the sequence of its digits, each digit is in a tens placeholder, let's write it like a sub n times 10 to the n, a sub n minus 1 times 10 to the n minus 1, all the way down, so on and so forth. And since this is x, and we're assuming that x is divisible by 9, this expanded form is also divisible by 9. What are we trying to prove? We're trying to prove that the sum of its digits is also divisible by 9. The sum of its digits would be a sub n plus a sub n minus 1 all the way down without the powers of 10 out front. So we need to remove them somehow. Well, we can do that by subtracting a number of 9s out front, so there would be just 1 left in front of every single digit. Every single digit would have a coefficient of 1 if we subtract this quantity. Performing this difference gives us the sum we're looking for, the sum of the digits of x. And actually, since we subtracted in this fashion, notice that we've subtracted a quantity whose coefficients were all multiples of 9s. The quantity we subtracted is divisible by 9. We assumed that our number x was divisible by 9, and so the difference of two numbers, both of which are divisible by 9, is also divisible by 9. And we've proved what we wanted to prove in this direction. Let's prove the other direction. Let's prove the converse. We'll leave our notation for x, and this time we'll assume that the sum of the digits are divisible by 9. That is, if we take the sequence a sub n minus 1, and so on, add them up, we're assuming this is divisible by 9. What do we want to show? We want to show the number itself, the number x, is also divisible by 9. Remember, we can express x in that nice expanded base 10 form like before. That's what we want to show is divisible by 9. And this direction of the proof is very similar, yet going in the other direction. We have this expression for the sum of the digits, yet we want to create the number itself. How should we do that? Well, this time we can add on the sum of the digits with all of these 9 coefficients. If we perform this sum, we would have 1 plus as many 9s needed in order to create the number x itself. And this addition of the sum with many 9 coefficients is divisible by 9. That's because every number was a multiple of 9. And we assumed that this sum, the sum of the digits, was divisible by 9. If we have two quantities both divisible by 9, then their sum is also divisible by 9. And that sum happens to be x, which is what we wanted to show. We wanted to show x is also divisible by 9. Hence, we've proved the converse of our statement. We proved this both ways. We've completed our if and only if proof. I'm sure you'll enjoy these proofs more and more if and only if you're a mathematician. In this video, we'll look at proof by contradiction, a very powerful proof technique indeed. Proof by contradiction works like this. We actually assume the opposite of what we believe is true. And from that assumption and through our logical reasoning process, we arrive at a contradiction, something that can't be true. Well, if we arrive at this contradiction via a logical true process, then the thing that must really be wrong is our assumption. And so, in fact, we can conclude our assumption was false, hence proving what we wanted to prove in the first place. We've actually already seen a proof by contradiction in our very first video. We showed that the square root of 2 was irrational by contradiction. We assumed the opposite of what we wanted to show. We assumed square root of 2 was rational. And through our logical argument, we found a contradiction. Our argument wasn't incorrect, it was our assumption that was incorrect. And then we concluded square root of 2 was indeed irrational. Let's do another example with the square root of 3. Let's prove the square root of 3 is irrational in a very similar way. Here's how proof by contradiction goes. We want to show square root of 3 is irrational. So let's suppose the opposite. Let's suppose square root of 3 is rational. What does this mean? Square root of 3 can be written as a ratio of two integers, m over n, and we're assuming that this is in reduced form. That is that m and n have no common factors. This is a reduced fraction. What does this mean? Squaring both sides means 3 equals m squared over n squared, or 3n squared equals m squared. M squared equaling 3n squared means m squared is a multiple of 3. And so is m. If a number's square is a multiple of 3, the number itself is also a multiple of 3. So we could say m equals 3 times k, where k is some integer. Let's plug this back in. So 3n squared equals 3k all squared, or 3n squared equals 9k squared. Which is the same thing as saying n squared equals 3k squared. N squared is a multiple of 3. So is n. N is also a multiple of 3. We concluded that m is a multiple of 3, and n is a multiple of 3. In other words, both m and n are multiples of 3, they're both divisible by 3. So the fraction m over n was not in lowest terms, it was reducible by a factor of 3. Contradicting our assumption. Sometimes when a contradiction is made, we'll see these dueling swords or crosshairs to show a contradiction happened. And since we have such a contradiction with our logical argument, our assumption must be incorrect. That the square root of 3 is not rational, we conclude square root of 3 is indeed an irrational number. Here's another somewhat fun example. Prove that the square root of 2 plus the square root of 6 is less than the square root of 15. Now I suppose you could verify this with a calculator, just punch in the numbers and see what you get, but that's not exactly satisfying, and that's not rigorous enough for a mathematical proof. So assuming we have no calculators available, and you're forced to prove this by hand, proving it by contradiction is quite easy. All we have to do is assume the opposite of what we like to show. Let's assume, by way of contradiction, that the square root of 2 plus the square root of 6 is greater than or equal to the square root of 15. Notice how this is the negation of what we want to show. We're not only reversing the direction of the inequality sign, we're also making it an or equal to statement. We have our assumption. Let's try to find a contradiction. How about we square both sides? Maybe we'll get a better idea of what these numbers are. On the right, the square of root 15 will simply be 15, and on the left, we'll have to do some distribution. Root 2 times root 2 is 2, root 6 times root 6 is 6, so we get 8, and then 2 times we'll have root 2 times root 6, or 2 root 12. Subtract both sides by 8, so 2 root 12 is greater than or equal to 7. And squaring both sides once more, on the left, 2 squared is 4, times root 12 squared is 12. I think we'll get 48 on the left, and 7 squared is 49 on the right. And so 48 is greater than or equal to 49. Clearly, this is a contradiction. 48 is not greater than or equal to 49. That's a contradiction. What went wrong? None of our logical steps were incorrect. It must be the assumption that was incorrect. Our assumption that the square root of 2 plus the square root of 6 is greater than or equal to square root 15 is incorrect. Since that assumption is incorrect, it must be that the square root of 2 plus the square root of 6 is indeed less than the square root of 15. Here's one of my all-time favorite proofs. We're going to show there's infinitely many prime numbers. Remember, a prime number is a whole number whose only factors are 1 and itself. You might also know that every whole number has a prime factorization and can be written as a product of primes. We'll have to use this as a lemma to prove our theorem. So here we go, theorem, there are infinitely many prime numbers. Let's prove it by way of contradiction. Let's assume there are finitely many primes. We don't know exactly how many there are, we're just assuming there are finitely many of them. Let's say there are n prime numbers. And since prime numbers increase in order, starting with 2, we can write them as a list. P1, P2, P3, all the way up to P sub n. This will be our list of every single prime number. Here's the trick to this proof. We're going to define a new number, capital N, as 1 plus the product of all the primes in our list. So n is P1 times P2 times P3 all the way up to Pn plus 1. Now I argue clearly n itself is not prime. Pn was the largest prime number, and n is much larger than Pn. It's the product of all the primes plus 1, so it's not prime being larger than the largest prime number. But we know from our lemma that every number has a prime factorization. So n must have a prime factorization. In particular, one of the primes on our list must be a factor of n. And if this number is a factor of n, it must also divide n. And since our prime number which divides n is also in our list of primes, it must divide the product, P1, P2, all the way up to Pn. It's somewhere in there, so it has to be able to divide into it evenly. Since this particular prime divides n, and it divides this product, it must divide their difference. And it just so happens that the difference between n and this product equals 1. So this prime divides the left-hand side, it must divide the right-hand side. This prime must divide 1. But the lowest prime number is 2, and 2 doesn't divide 1. No prime number can divide 1, and so this is impossible. This is a contradiction. There wasn't anything wrong with our line of reasoning, yet we found a contradiction. It must be that our assumption was wrong. In fact, there are not finitely many primes, there are infinitely many primes. I'm sure with a little bit of practice, you'll love this proof technique just as much as I do. But I don't want to contradict anything. A theorem is only a theorem if it's true 100% of the time. If there's even just one tiny thing about the theorem statement, one little thing that's wrong, well, we can't consider it a theorem any longer. In some sense, that makes theorems easy to disprove if you have a counterexample. One example of a statement not being true is enough to invalidate it from being a theorem. Thus, if you'd ever like to disprove something, all you need to do is find one example for which the theorem, or I should say supposed theorem, is not true. Here's a simple example of a false theorem. Every college student is from the United States of America. How do you suppose you would disprove this? Well, all we need to do is find a counterexample. Simply find one student who attends college but is not from the United States. Throughout my own studies, I met plenty of people from all across the world in the same college classes I was in, and so just one of them is enough to disprove this statement as a counterexample. Here's a tougher, more mathematical one. Every positive integer is equal to the sum of two integer squares. This would be pretty challenging to prove, in particular because it's not true. Simply look at the case of 3. 3 is a positive integer, but it cannot be written as the sum of two square integers. If we wanted to sum two integers to get 3, the only possibilities would be 0 and 1. Since we're squaring them, 2 wouldn't work because 2 squared would be 4, and that would already be too large. So we would have to work with 0 and 1, or -1. But squaring all of these in any combination would never give us 3. We didn't have to look too far for an example to disprove this conjecture. Just look at 3. 3 cannot be written as the sum of two integer squares, hence this conjecture is false by counterexample. Here is another one. Let's let n be a natural number, and suppose n is prime. The claim is that 2 to the power of n minus 1 is also prime. The problem with many conjectures is that they feel very true. This feels pretty true, and if you try a number of examples, you might believe it's true as well. If you start going through prime numbers, starting with 2, well, 2 squared minus 1 is 3, which is prime. The next prime number is 3. 2 to the third minus 1 is 7, which is prime. The next prime number is 5. And 2 to the fifth minus 1 is 31. That's also prime. This conjecture feels true. But examples are not proofs. We would need a formal proof to actually verify this conjecture, and that's not going to happen because it's not true. Take the counterexample 11. 11 is prime, and 2 to the 11th power minus 1 can be written as 23 times 89. In other words, a composite number, it's not prime. And hence, by this one example, granted we have to dig a little bit to find that example, we have disproved this statement. Anytime you want to disprove something, it suffices to find one example where the statement is not true. Sometimes it's very difficult or even impossible to prove an entire theorem at once. In those situations, it's a lot easier to break the theorem into different cases and prove each case. This is known as proof by cases or proof by exhaustion. If we prove every possible instance of a theorem, then that theorem is proven. Here's an example. Prove for any integer n, n squared plus n is even. Here's the proof. Suppose n is an integer. We want to show n squared plus n is even. That is, n squared plus n can be written as twice an integer. Thing is, we don't know anything about n itself other than it's an integer. And there are two possibilities here. Case 1, n is even. Case 2, n is odd. If n is even, we can write n as twice another integer. That's what it means to be even. Now we can find an expression for n squared plus n, assuming n is even. If n is 2k, then our expression is 2k all squared plus 2k. Using properties of exponents, that's 4k squared plus 2k. We want to write this as twice an integer, factor out a 2. Since k is an integer, 2k squared plus k is also an integer, and n squared plus n is twice an integer, hence is even. That's the first situation, that's the first case. What about if n was odd? That means n can be written as 2l plus 1 for some integer l. Now write our expression, n squared plus n. That would be 2l plus 1 all squared plus 2l plus 1. We'll have to expand this using our rules for distribution and combine any like terms. We want to show that this is also an even number, that it's twice an integer. Fortunately, everything has a factor of 2. We can factor a 2 out. 2l squared plus 3l plus 1, that's an integer since l is an integer. Thus, n squared plus n can be written as twice an integer and is even. When we assumed n was an integer, there were only two possible cases. N was even or n was odd. Both of those cases resulted in n squared plus n being even, and we have proved our theorem. Here's another example. Prove x plus the absolute value of x minus 7 is greater than or equal to 7 for all real numbers x. Letting x be a real number, we don't know what x is, and we don't know how x is going to interact with this expression. Since we're dealing with an absolute value, we know that the absolute value of a positive number is just that number, and the absolute value of a negative number is the positive of that number, the negation of that number. So it looks like the cases will split whether x is greater than or less than 7. If x is greater than or equal to 7, then x minus 7 is greater than or equal to 0, positive, and hence the absolute value doesn't do anything. The absolute value of x minus 7 is just x minus 7. Hence, in this case, x plus the absolute value of x minus 7 is just x plus x minus 7, which is 2x minus 7, and assuming that x is greater than or equal to 7, this expression must be greater than or equal to 14 minus 7, which is 7. Thus, the original expression has to be greater than or equal to 7. The other case that can happen is if x is less than 7, meaning x minus 7 is less than 0, and when we apply an absolute value to it, since it's negative, the absolute value has the effect of negating that expression. Thus, x plus absolute value of x minus 7 turns into x minus 7, which is just 7, and is indeed greater than or equal to 7. We broke our theorem into two possible situations. Either we're in case 1 or we're in case 2. Since they're both true, it's true for all real numbers x. We've proven this statement. Here's one more famous theorem every aspiring math student should know, the triangle inequality. For two real numbers x and y, the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. How should we prove this? Let's break it into cases on x and y. We'll break it into three different cases. Case 1, x and y are both greater than or equal to 0. Case 2, x and y are both less than 0. And case 3, one of the variables is positive and one is negative. Let's just say x is greater than or equal to 0 and y is negative. Now, we're going to say without loss of generality here. What does that mean? Well, since x and y were arbitrary, proving x positive with y negative is the same proof as y positive and x negative. We don't need to write the argument twice since it would be exactly the same thing. You'll see this without loss of generality, or WLOG, sometimes when we're doing proofs like this. Let's look at the three cases, keeping in mind the definition of the absolute value. The absolute value of x is x when x is greater than or equal to 0. The absolute value of x is negative x when x is less than 0. Thus, in our first case, the absolute value of x plus the absolute value of y is x plus y. Since we assumed x and y were both greater than or equal to 0, and since they're both positive, their sum is positive, which is the same as the absolute value of the sum. Since in this case, the absolute value of x plus y equals the absolute value of x plus the absolute value of y, we can also say this is less than or equal to. On to the second case. Both x and y are negative. So the absolute value of x is negative x. The absolute value of y is negative y. And x plus y is also negative. So the absolute value of x plus y equals negative x plus y, which is negative x plus negative y, and equals the absolute value of x plus the absolute value of y. And so in this case, we also have equality between the absolute value of x plus y and the absolute value of x plus the absolute value of y. We can also say greater than or equal to. Here's the trickiest case. One is greater than or equal to 0, we'll call it x. The other is less than 0, we'll call it y. So the absolute value of x is x, the absolute value of y is negative y. And we actually have two subcases in this case. X plus y could be greater than or equal to 0, or x plus y could be less than 0. In both cases, it works out. If x plus y is greater than or equal to 0, then the absolute value of x plus y is x plus y, which is less than x plus negative y, since y is negative. And also, x equals the absolute value of x, since x was positive,
Negative y equals the absolute value of y, since y was negative, and we have exactly what we want. The absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. Here's the final case. X plus y is less than 0, where x is greater than or equal to 0 and y is less than 0. The absolute value of x plus y must be negative x plus y, since their sum is negative, which is negative x plus negative y, which is less than or equal to positive x plus negative y. Negative x is less than or equal to positive x. Since x is positive, x equals the absolute value of x. Since y is negative, negative y equals the absolute value of y. And once again, we have what we want. The absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. We have proved the triangle inequality for every possible case, thus it's true in general for all real numbers x and y. That's not the only proof of the triangle inequality, but I think it's a great one to illustrate proof by cases or proof by exhaustion. And let me tell you, I'm exhausted. How would you knock down an infinite line of dominoes? Well, you'd have to knock down at least one domino yourself. You'd knock down the first domino. And then you'd just have to check that if a domino is knocked over, it knocks over the next domino. If those two things happen, well, the dominoes would fall forever. This is the idea behind the proof technique of mathematical induction. Here's what mathematical induction says. If P of n is a statement for each natural number n, and P of 1 is true, this is often called the base case, which we check. And 2, if P of k is true for arbitrary k, implies that P of k plus 1 is true. This is called the induction hypothesis. Then we say the statement P of n is true for all natural numbers. Essentially, the first step is just saying knock down the first domino, and the second step is saying check that if a domino is knocked over, the next domino is knocked over. Let's look at some examples. We're going to prove, using mathematical induction, this statement, our statement P of n, that the sum of the first n natural numbers equals n times n plus 1 over 2. There are many ways to prove this, but it's a great first induction proof. We're letting our statement P of n be the sum of the first n natural numbers, and we're claiming that equals n times n plus 1 over 2. Start with the base case. Typically, the base case is the first number. Here our base case will be n equals 1. Let's check that this is true. P of 1 is the sum of the first natural number, which is just 1. And let's check that this equals n times n plus 1 over 2. That would be 1 times 1 plus 1 over 2. Hey, that's actually 1. And so we've checked our base case. P of n holds true for n equals 1. That's the first step. Now comes the induction step. We assume that the kth domino has fallen, or in this case, we assume P of n is true for k. What that means here is that we know, take it for a fact, that the sum of the first k natural numbers equals k times k plus 1 over 2. Who knows if it's true for other values, but we assume it's true for k. Using this assumption, we have to show our statement is true for k plus 1. Since we want to show that our sum holds true for the first k plus 1 natural numbers,
Let's write the sum of the first k plus 1 natural numbers. Now, we don't necessarily know what this is, but we do have the assumption of the first k natural numbers. By assumption, by our induction step, we know that this is k times k plus 1 over 2. That's what we assumed. And so the sum of the first k plus 1 numbers is k times k plus 1 over 2 plus the k plus 1. Now our job is to write it in the form that we want, the form of our pattern. And it really just comes down to algebra. Let's combine these using a common denominator. So k times k plus 1 plus 2 times k plus 1 can all be over 2. And fortunately, we can factor out a k plus 1. So k plus 1 times k plus 2 over 2, we know this equals the sum of the first k plus 1 natural numbers, but it's not quite in the form we're looking for. If you look at our statement, p of n, and we plugged in k plus 1, it would look like k plus 1 times k plus 1 plus 1 all over 2. Well, with just a little sleight of hand, we can break up the 2 as 1 plus 1 and get exactly that. Since we assumed our statement was true for n equals k, and then we showed it implied it was true for k plus 1, we completed the induction step. Using that along with our base case proves the statement for all natural numbers. We head over the first domino with the base case, and we head over every other domino with the induction step. Here's another example. Prove by induction 3 to the n minus 1 is a multiple of 2. Here's our statement. P of n says 3 to the n minus 1 equals 2 times some number. We have to prove the base case, so let's do it for the first natural number, 1. P of 1 would say that 3 to the first minus 1 is 3 minus 1, that's 2, and 2 happens to be 2 times 1. So indeed, this is a multiple of 2, and we've proved our base case. Now for the induction step. We assume our statement is true for n equals k, or that we assume that 3 to the k minus 1 is a multiple of 2. We're going to treat this just like a fact. What we want to show now is our statement is true for k plus 1, or in other words, 3 to the k plus 1 minus 1 is a multiple of 2. How can we show 3 to the k plus 1 minus 1 is a multiple of 2, knowing for a fact 3 to the k minus 1 is a multiple of 2? We somehow have to maneuver this so the 3 to the k minus 1 pops out and we can use it. Well, it just so happens 3 to the k plus 1 can be written as 3 times 3 to the k. So we're a little closer, but we still don't have a 3 to the k minus 1. How about we just say 3 times 3 to the k is 2 times 3 to the k plus 3 to the k. Now we see our assumption, 3 to the k minus 1, we know that this is a multiple of 2. Let's just write it as 2 times m. So 3 to the k plus 1 minus 1 equals 2 times 3 to the k plus 2m. Factor out a 2, and we have 2 times 3 to the k plus m. But this is 2 times a number. In other words, it's a multiple of 2. So 3 to the k plus 1 minus 1 is indeed a multiple of 2 when 3 to the k minus 1 is a multiple of 2. We've proven our induction step. We already did the base case. Our statement is true for all natural numbers n by mathematical induction. Let's prove one more very famous, very powerful result. This is known as de Moivre's theorem, and here I is the imaginary unit, the square root of -1. This is our statement P of n. If we want to prove it, we need the base case. We have to show it's true for n equals 1. So let's let n equal 1. That means cosine theta plus I sine theta all to the first would equal cosine of 1 theta plus 1 times sine of 1 theta. And that's true. We have our base case. On to the induction step, we assume it's true for n equals k. In other words, we assume cosine theta plus I sine theta all to the k equals cosine of k theta plus I sine of k theta. We're taking this as a fact, and we want to show it's true for n equals k plus 1. We want to show cosine theta plus I sine theta all to the k plus 1 equals cosine of k plus 1 theta plus I sine of k plus 1 theta. If we want to show that this is true, we're going to have to pick one side of the equation to start with, and somewhere along the way we're going to need our induction hypothesis to show up. Starting with the right-hand side, to me, it's not entirely clear where we would go from here. Let's start on the left-hand side and use a similar trick. Let's break this up as cosine theta plus I sine theta all to the k times cosine theta plus I sine theta to the first. This is just using properties of exponents. And hey, there we go. There's our induction hypothesis. We're assuming cosine theta plus I sine theta to the k equals cosine of k theta plus I sine of k theta. Here's where a bit of hand cramping comes in. Let's go ahead and just distribute everything. We would have cosine of k theta times cosine theta. We'd have cosine k theta times I sine theta. We'd have I sine k theta times cosine theta. I sine k theta times I sine theta. The thing to keep in mind here is that the imaginary unit I, which represents the square root of -1, implies that I squared is -1. So we can replace I squared with -1. And it's common practice to group by real part and imaginary part. That is, we should say cosine k theta minus sine k theta sine theta is its own grouping, and sine k theta cosine theta plus cosine k theta sine theta is its own grouping with an I attached. And if you think back to those lovely trigonometric identities, specifically the sum and difference identities for sine and cosine, you might notice that these follow those rules exactly. The real part of this equation is just the expanded form of the identity for cosine of a sum, and the imaginary part is just the expanded form of sine of a sum. Factoring out theta gives us exactly what we want. We have proved the induction step. We assumed it was true for n equals k, and we showed it was true for n equals k plus 1. That, along with the base case, proves our theorem for all natural numbers n. Did you know if you watch one video in this series, you'll have to watch the next? And you've watched this video, so let me induce you to watch the next one. In this video, we're going to talk about strong mathematical induction. What's strong induction? Well, it's essentially like regular mathematical induction. We need to make sure our base case is true, and we need to do the induction step. The difference being, with regular mathematical induction, we assume P of k is true implies P of k plus 1 is true for a specific k. Strong mathematical induction assumes that our statement is true for every value before k. That implies P of k plus 1 is true. If we have these two facts, then we have a proof by strong mathematical induction. Here's an example. Let's prove any integer greater than 1 can be expressed as a product of prime numbers. Our base case will be n equals 2, and this is true since 2 is a prime number and can be written as 2 times 1. 2 is a prime number, and although 1 isn't technically a prime number, it's still represented as a product of primes here. On to the induction step, and since we're using strong induction, we assume that our statement is true for all values less than k plus 1. We're assuming our statement is true from 2 up to k. We want to show this implies our statement is true for k plus 1. In other words, we need to show k plus 1 is a product of primes. And we have two possibilities here. Either k plus 1 is prime, and we're done, since itself is a product of prime numbers, 1 and itself. The other possibility is that k plus 1 is not prime. Hence, it's a composite number, and k plus 1 is divisible by an integer. Call it a. A has to be strictly greater than 1 and strictly less than k plus 1 in this scenario, and there has to be some other integer b that also has to be strictly less than k plus 1, since these two numbers a and b have to multiply to k plus 1. This is a very fancy way of saying k plus 1 is not prime. It's written as two numbers, the product of two numbers, less than itself. And by our induction hypothesis, since a and b are both less than k plus 1, they can be expressed as a product of prime numbers. Hence, k plus 1 is the product of prime numbers, and we've satisfied our induction hypothesis. That, along with our base case, proves our theorem. Now that you know how to use strong induction, I strongly recommend watching the next video in this course.
Welcome to this lesson on functions. What exactly is a function? Well, it's just a mapping, an assignment, or a rule from one set to another. Here we take elements in a set A, called the domain, and map them or assign them to other elements in the set B, called the codomain. And it's important we specify that each element in the domain gets assigned to exactly one element in the codomain. While the codomain is all possible outputs, you may be familiar with the range. The range is the set of all the actual outputs that the function produces. It's a subset of the codomain. It's nice to sometimes visualize functions like this. Here we have an element x in the domain A getting mapped to the element y in the codomain B by this function f, by the rule. There are some special type of functions that we talk about when we're doing function proofs. The first type of functions are injective. Essentially, this means that distinct inputs are mapped to distinct outputs. The math definition, or at least one way to say the definition, is that for any two elements x1 and x2 in the domain, if the outputs f of x1 and f of x2 are the same, that must mean that x1 and x2 are the same. Distinct inputs have distinct outputs. We also have surjective functions. This essentially says that every element in the codomain is mapped onto by one element in the domain. Every output has at least one input, or there exists an element in the domain such that f of x equals y for each element in the range. Sometimes we also call injective functions into, and sometimes we call surjective functions onto. When a function is both injective and surjective, we call that function bijective, saying that there is a one-to-one correspondence between the sets, the domain, and the range. Let's get our hands dirty with some function proofs. Here we'd like to prove that the function f mapping from the real numbers to the real numbers, that's our domain and codomain, defined this way, f of x is 2x plus 3, we'd like to prove that this function is injective. In other words, distinct inputs create distinct outputs. In other words, we want to show if a and b are in the domain and f of a equals f of b, we'd like to eventually show a equals b. This is the definition of an injective function. So assume f of a equals f of b, and just substituting these values into the function, f of a is 2a plus 3, f of b is 2b plus 3, and we're assuming that these equations are equal. Doing a little bit of algebra won't hurt here. Subtract 3 from both sides, and a division by 2 shows a equals b. We assumed f of a equals f of b. We concluded a equals b. By definition, this function is injective. How about a surjective proof? We'd like to show that this function g, which maps the real numbers onto the real numbers and defined by g of x is x cubed, is surjective. In other words, we want to show for every element y in the real numbers, there exists some x in the real numbers, some element in the domain, such that g of x is y. Well, since the function is x cubed, just select any old y in the real numbers and set it equal to x cubed. And a little bit of algebraic manipulation, we can say that x is the cubed root of y. This x is the element to plug into the function to produce y. In other words, regardless of the y we select, plug the cubed root of y into the function and we'll attain it. This function is surjective. Let's end on a bijective proof. We'd like to show x squared defined from the non-negative real numbers to the non-negative real numbers is a bijection. This is a bijective function, meaning it's injective and surjective. Select two arbitrary elements, a and b, in the domain and set their outputs equal. That is, we assume h of a equals h of b. What's h of a? According to the function, it's a squared. H of b is b squared. These are equal by assumption. We'd like to say a equals b. That would make the function injective. Can we say that here? Well, yes, we can, because of the domain and range of this function. We were only dealing with non-negative real numbers. We don't have to deal with any plus or minus square root business here. A squared is b squared definitely implies a equals b if we're only talking about non-negative real numbers. This function is injective. How about surjective? We want to show for every element y in the non-negative real numbers, there exists some other element x in the non-negative real numbers such that the function evaluated at x is y. How can we do that? Select the element x equals root y, because when we evaluate the function at root y gets squared, and we end up with y. Notice how our job for these surjective proofs is to find an element to plug into the function to output just y. And that usually has to do with inverting the function. Here, the inverse of the square function is the square root function. We've shown that this is a surjective function now, and since it's injective and surjective, this is a bijective function. We've functioned pretty well today, navigating the domain of math. Let's arrange another meeting soon.
Let's talk about existence proofs. These I find pretty fun because the theorems might be as simple as there exists a blank, and your job is to find that thing. Finding it might be a challenge, but the idea is easy. Once we find an object of those characteristics, we're done. It exists. Here's a fairly straightforward example. Theorem, there exists an integer n with the property the absolute value of n squared minus 5 is less than or equal to 1. Although you might not think of this as a proof, you might see this in a pre-calculus class, because that's essentially how we're going to solve it. We have this absolute value equation to solve, and this is what I would write down on my scratch paper. If this absolute value is less than or equal to 1, that means minus 1 is less than or equal to n squared minus 5 is less than or equal to 1. Or n squared is less than 6, greater than 4, or square rooting. We need an integer in this interval, so I think n equals 2 works just fine. And so for the actual proof, I would just say let n equals 2, then the absolute value of 2 squared minus 5 equals 1, and we've satisfied the property. The proof is actually very, very short. The scrap work, which you might throw away, is just a little bit more computational. Let's try another existence proof, and I think this is one of my absolute favorites. Let's prove there exist two positive irrational numbers, call them s and t, such that s to the power of t is rational. This is a bit counterintuitive. If we have two irrational numbers, raising one to the power of the other, how could it ever be that this is rational, can be written as a fraction? But in fact, there are many numbers that satisfy this. We just have to find two. Off the top of your head, if you haven't done a whole lot of mathematical exploration, you might not know a whole lot of irrational numbers. But one irrational number we do know from this course is the square root of 2. Let's take s to be the square root of 2. And we need another number to put in the exponent of square root of 2, another irrational number. Well, what about the square root of 2 again? There's nothing saying we can't choose the same number twice. Let's take s equal to t equal to the square root of 2. That makes s to the power of t root 2 to the power of root 2. Now, I don't know what this is. We could use a calculator, but that doesn't really help us, not with mathematical proofs. And so really there are two cases here. Root 2 to the power of root 2 could be rational. And if that's the case, we're done. We've completed the proof. Otherwise, root 2 to the power of root 2 would be irrational. In which case, we have another irrational number at our disposal to try to prove this theorem. So in this mini case, let's just pretend we're starting over. Let's find two irrational numbers where one to the power of the other is rational. And let's take s to be root 2 to the power of root 2. We're assuming that this is irrational in this case. And let's take t to be regular root 2 again. In this mini case, we have two new numbers, each of which are irrational. Raise one to the exponent of the other. That's root 2 to the root 2, all to the root 2. And thankfully, in this case, properties of exponents come to our aid. Exponent to an exponent, we multiply those. Root 2 times root 2 is 2. And then root 2 squared is 2, which is rational. And we've actually proved this. Either root 2 to the root 2 is rational, or root 2 to the root 2 to the root 2 is rational. And I just think that's absolutely incredible that we proved this. We found two numbers, both of which are irrational. When you raise one to the power of the other, it's rational, even though we don't even know what root 2 to the root 2 is. Yet, it exists. It's right there. Here's another slightly harder example. Theorem: between every two rational numbers, there exists an irrational number. Let's use the lemma that if we take a rational number plus an irrational number, that's also irrational. Also, if we take a rational number times an irrational number, it's irrational. That's not too tough of a lemma to prove. I'll leave it to you as an exercise. For this example, we'll just take this lemma as a fact. Here's the proof. We need two rational numbers, so let's let x and y be two rational numbers. Without loss of generality, let's say x is less than y. This just means the proof would be exactly the same if y was less than x. But we don't want to write the same proof twice, so we say without loss of generality. And we need some measurement, some way to count the in-between of these numbers. Typically that's done through the distance, the difference between them. Let's let d be y minus x. This will be the distance between the two numbers. We have two rational numbers, we have the difference between them, and we know that combining a rational number via addition or multiplication with an irrational number produces an irrational number. How can we combine these facts to find an irrational number between x and y? Well, let's use our trusted friend, the irrational number square root of 2. We know square root of 2 is irrational. So maybe there's a way to start at x, use square root of 2 to be a little bit more than x, but less than y. So you might want to try x plus square root of 2. This is certainly irrational because x is rational, root 2 is irrational, and if we sum a rational plus an irrational, the result is irrational. However, this might be greater than y. We don't know since we picked y arbitrarily, so this won't quite cut it. Now, you could try shrinking square root of 2 by dividing it by larger and larger numbers, but since we don't know y, we still don't know how small we need to make root 2. Except we know the difference between x and y. So we set it like this. Take root 2 over 2. This is irrational, since it's an irrational number multiplied by 1/2, a rational number, and this value is about 0.7. In particular, it's less than 1. Multiply this by d, d being the distance between x and y. Now, this is a rational number, d, multiplied by an irrational number, root 2 over 2, and so this quantity is irrational. And since it's d times 0.7, it's not quite the full distance d. So if we add x to it, it's not going to get us to y. That is, x plus d times root 2 over 2 is less than y, and this number is irrational. It's a rational number x plus an irrational number d times root 2 over 2. And we've found our result. This value, which is x plus d times root 2 over 2, is an irrational number in between x and y, both of which are rational. I hope you've seen just how fun these existential proofs can be. You might have to do a little bit of tinkering, finding your way in the dark, but I promise you'll find the proof exists.
Now that we've looked at existence proofs, let's look at uniqueness proofs. That's proving there's an element that satisfies a certain condition, and it's the only one that does so. Essentially, these proofs are broken into two parts. First, we need to show that this thing exists. Then we have to show it's unique. Not only does it exist, but there's no others like it. Here's a fairly quick example. Prove that 2 is the unique positive number, which is both prime and even. Now, 2 certainly exists. It's definitely a positive number. It's also definitely prime and even. 2, by definition, is an even number. It's divisible by 2. And by definition, it's prime. Its only divisors are 2 and 1, itself and 1. Thus, this thing exists. We need to show it's unique under these conditions. So let's suppose, for argument's sake, that there's some number n which satisfies these conditions, that it's positive and prime and even. Since this supposed n is even, it's divisible by 2. But since n is prime, it's only divisible by 1 and itself. Its only divisors are 1 and 2. Thus, 2 and n must be the same number. N must be 2. This is the only number which satisfies this condition. It's unique. Let's look at another example. Intuitively, you know for linear equations, if a solution exists, it's unique. That is, we're assuming in this equation a, r, and b are not 0. None of them are 0. This should certainly have a unique solution for r. But have you ever wondered why it's unique? Well, let's prove it. First, we need to show it exists. This is just a little bit of regular algebra. Subtract b from both sides and divide by a. There's a solution. R is minus b over a. It exists. Again, we're assuming a, b, and r are not 0 here, so this definitely exists. Now we have to prove it's unique. How can we do that? Well, let's assume that there's another solution to this equation. Let's say that r and r prime both satisfy this equation, and let's solve for r prime. In fact, the algebra is exactly the same. R prime is minus b over a. What have we shown here? R is minus b over a. R prime is minus b over a. R equals r prime. That is, if we assume there was another solution, it turns out that that solution was the original one unique solution, r. This is proven. Here's a slightly tougher example. Consider the function f going from a to b, and let's suppose it's a bijective function. What we'd like to show is that there's a unique function g going from b to a, the other way, such that the composition g of f of x equals x for all x in a, and f of g of y equals y for all y in b. That's a little bit of a mouthful, but essentially this statement is saying that inverse functions are unique. Let's break it down. First, we need to prove this exists. Since f is bijective, by definition, f is injective and surjective. Intuitively, that means unique inputs produce unique outputs. And the function f can reach every element in B. Here's the mathematical way of saying that. For every y in B, for every element in the set B, there exists some unique element x in A that we can plug into f of x to produce y. That's what it means to be injective and surjective. Now we need to be a little bit tricky. We want to create the situation posed in the problem. I essentially want to evaluate the f function at g of y and get y. I essentially want to evaluate the g function at f of x and get x. So define it like that. Let's define g of y to be x for each y in B. Then we have exactly what we want. F of g of y is the same as f of x, because g of y is x. And f of x equals y for all y in B because of that bijective statement. Furthermore, if f of x is y, then g of f of x is g of y, which is x, for every x in A. This is exactly what it means for g to be the inverse of f. This exists. Now that we've proven the inverse exists, we want to prove it's unique. How do we do that? Let's suppose there's another function, call it h, going from the set B to A, such that h of f of x is x for every x in A, and f of h of y is y for all y in B. This is essentially the restatement of the problem, just with another function h that has the same property. Let's think about what we want to show. We essentially want to say that this new function h really is just the g function, that they're equivalent. So let's say for all y and b, g of y, and we want this to end up being h. Well, by this statement, what is y? Y is f of h of y. That means g of y is g of f of h of y. Yet we already know g and f are inverse functions. What happens when we compose inverse functions? They essentially undo each other. When we compose g with f, they undo each other. We just get what's on the inside, the argument, in this case, h of y. Since this is true for every y and b, these functions are the same. G actually is h, and we've proven that inverse functions are unique. I hope you hung in there for that example, because I think you're really unique.
In this video, we'll discuss false proofs. A false proof is one that, on the surface, might look correct, but ultimately has an error in it. Once you spot that error, that illogical step, we can conclude that the proof is in fact invalid, and we don't have to accept the result. Take a look at this famous false proof, and see if you can spot the error. Let's start with just saying a equals b. Multiply both sides of this equation by a. A times a will be a squared on the left. Next, subtract b squared from both sides. And we'll go ahead and factor. On the right-hand side, there's a greatest common factor of b. We can factor out a b from both terms. On the left, we have the difference of squares formula. This will factor into a plus b times a minus b. Hey, look at that! There's a factor of a minus b on both sides. Let's cancel a minus b on both sides. This leaves us with a plus b equals b, but at the start we assumed that a equals b. So really on the left we have b plus b equals b, or 2b equals b. And dividing both sides by b gives that 2 equals 1. This is a problem if you want to use numbers effectively. But what illogical step did we use here? We seem to be able to follow all the basic rules of algebra. What went wrong? Well, there is a hidden division by 0 in this setup. We assumed at the start that a equals b. So if we have the factor of a minus b and a equals b, then these are both zeros. And when we cancel them, we're effectively dividing by 0. That's not allowed. And in fact, this is one of the consequences of sometimes allowing a division by 0, that you can make any number equal any other number. Make sure to watch out for divisions by 0 in your proofs. Here's another example. Think you can spot the error? -1 equals -1. This is certainly true. Divide both sides by 1. Now, although we traditionally leave the negative in the numerator, or maybe just to the left of the fraction, there's nothing wrong with just placing this negative symbol in the denominator. Square root both sides, and we'll need to pull a definition from complex analysis. If we're going to allow the square roots of negatives, we have to say that the square root of -1 is I. If we just apply our rules for radicals, that is, square roots, if we're square rooting a fraction, take the square root of the numerator over the square root of the denominator. Now the square root of +1 is +1, and we just pulled that definition that the square root of -1 is I. So I over 1 equals 1 over I. We might as well just say I equals 1 over I. No need to say division by 1. Moving things around, multiplying both sides by I, we would see that I squared equals 1. But since I is the square root of negative 1, that means that I squared is negative 1. And so now our equation says negative 1 equals 1. Were you able to spot the error? This one is pretty subtle. Our rules for radicals only apply when the argument is positive, when the inside of the square root is positive. We're not allowed to break up the square root like this. At least not in this case. The thing to watch out for is generalizing rules that you know to be true in certain situations. We tried to generalize a rule that just didn't apply in this case. Whenever you're reading and writing proofs, you have to make sure each and every step is completely justified. Otherwise, your argument will fall apart.